Imagine holding a snowball on a hot summer day. You know what happens, right? The ice melts. The snowball gets smaller and smaller until it's just water running through your fingers. That's not surprising. That's just physics. That's what's supposed to happen. But now imagine that snowball sitting in the blazing sun, hour after hour, day after day, and never melting. Not even a little bit. It just sits there, solid and frozen, completely ignoring everything we know about heat and ice. That would be impossible, wouldn't it? It would break the rules of nature. Scientists would be completely baffled. They'd want to study that snowball, figure out what's going on, understand why it's not behaving the way it should. Well, astronomers have found something just as impossible, just as baffling, except it's not a snowball. It's an entire planet. A world so close to its star that it should have been destroyed millions of years ago. The heat should have ripped it apart. The gravity should have torn it to pieces. Every law of physics we understand says this planet cannot exist. And yet, there it is, orbiting its star, defying explanation, challenging everything we thought we knew about how planets work. This planet has a name, WASP-12b, and for more than a decade, it has been one of the greatest mysteries in astronomy. Scientists have observed it with our most powerful telescopes. They've measured it, analyzed it, run countless computer simulations trying to understand it. And the more they learn, the stranger it becomes. WASP-12b is a world that should be falling apart right now, disintegrating before our eyes, scattered into space like ashes in the wind. But it's not. It's still there, still intact, still defying the laws of nature. Today, we're going to explore this mystery together. We'll journey to WASP-12b and discover what makes it so impossible. We'll learn about the forces that should be destroying it and why they're not. We'll meet the scientists who are trying to solve this puzzle and hear about their latest discoveries. And we'll confront the disturbing possibility that maybe, just maybe, our understanding of planets is not as complete as we thought. Because if WASP-12b can exist when it shouldn't, what else might be out there, hiding in the darkness, waiting to surprise us? To understand why WASP-12b is so strange, we first need to talk about a type of planet that shouldn't exist at all: hot Jupiters. The story begins in 1995, and it's a story that changed astronomy forever. For thousands of years, humans looked up at the night sky and wondered, are there other planets out there, orbiting other stars? Do other solar systems exist? For a long time, we had no way to answer these questions. The planets in our own solar system were easy to see because they're close and they reflect the sun's light. But planets around other stars would be incredibly faint, completely overwhelmed by the brightness of their parent stars. It would be like trying to spot a firefly next to a searchlight from miles away. But in the 1990s, astronomers developed clever techniques to find planets even when they couldn't see them directly. One method is called the radial velocity technique, and it works by watching the star, not the planet. When a planet orbits a star, the star doesn't stay perfectly still. The planet's gravity tugs on it, making it wobble slightly, like a spinning figure skater with their arm extended. This wobble is tiny, but it's detectable. As the star wobbles toward us and away from us, its light shifts slightly in color, becoming a tiny bit bluer when moving toward us, and a tiny bit redder when moving away. By measuring these shifts very precisely, astronomers can tell that a planet is there, and they can figure out how massive it is and how close it orbits. Two Swiss astronomers, Michel Mayer and Didier Queloz, were using this technique to search for planets around Sun-like stars. They were observing a star called 51 Pegasi, about 50 light-years away from Earth in the constellation Pegasus. And in October 1995, they announced something shocking. They had found a planet orbiting 51 Pegasi, but this planet was nothing like anything in our solar system. The planet, named 51 Pegasi b, was huge, about half the mass of Jupiter, the largest planet in our solar system. But here's what was shocking. It was orbiting incredibly close to its star, much closer than Mercury orbits our Sun. The planet completed one full orbit in just 4.2 days. Think about that. Earth takes 365 days to go around the Sun. Mercury, the closest planet to the Sun, takes 88 days. This planet was whipping around its star in barely more than 4 days. And because it was so close, it was hot. Incredibly hot. The temperature on this planet was estimated to be over 1,800 degrees Fahrenheit, hot enough to melt metal. Astronomers started calling planets like this hot Jupiters, gas giant planets orbiting very close to their stars. The discovery stunned the scientific community. According to all our theories of how planets form, hot Jupiters shouldn't exist. Here's why. Planets form from disks of gas and dust that surround young stars. Close to the star, it's too hot for gas to clump together to form giant planets. The heat from the star prevents it. Giant planets like Jupiter should only be able to form far from their stars, where it's cold enough for ice and gas to accumulate. In our solar system, that's exactly what we see. The small rocky planets, Mercury, Venus, Earth, and Mars, are close to the Sun. The giant planets, Jupiter, Saturn, Uranus, and Neptune, are far away. So how could a gas giant end up so close to its star? The only explanation was that these planets must have formed far away, where it's cold, and then somehow migrated inward, moving closer and closer to their stars over millions of years. But how? And why? These questions opened up entirely new areas of research in astronomy. After the discovery of 51 Pegasi b, astronomers started finding hot Jupiters everywhere. As detection techniques improved, hundreds of these worlds were discovered. Each one was a giant planet, often bigger than Jupiter, orbiting extremely close to its star. Some took only a few days to orbit. Some were so close that their atmospheres were being heated to thousands of degrees. Some were being stretched and distorted by their star's gravity into egg shapes. Hot Jupiters were not rare oddities. They were common. And this meant our understanding of how solar systems form was incomplete. Our solar system, with its orderly arrangement of small planets close to the Sun and giant planets far away, was not the standard model. It might even be unusual. The universe was full of planetary systems arranged in ways we never expected. Scientists developed theories to explain planetary migration. Maybe interactions with the disk of gas and dust could cause a planet to slowly spiral inward. Maybe gravitational interactions with other planets could throw a giant planet into a different orbit, one that took it closer to the star. Maybe both processes happened. Computer simulations showed that planetary systems are dynamic, chaotic places where planets can move around, collide, get ejected into space, or fall into their stars. This was exciting, but also troubling. If planets could migrate, if they could move from one orbit to another, then planetary systems were much less stable than we thought. A planet that formed in a comfortable orbit might not stay there. Over time, it could move, and if it moved too close to its star, bad things would happen. The star's heat and gravity would start to affect the planet. The planet's atmosphere could start to boil away into space. The planet could get stretched and deformed. And eventually, given enough time, the planet might be destroyed completely, torn apart by forces it couldn't resist. Hot Jupiters were living on the edge, in a dangerous place where survival was not guaranteed. And among all the hot Jupiters discovered, there was one that stood out as particularly doomed, a planet that absolutely should not still exist. That planet was WASP-12b. WASP-12b was discovered in 2008 by an international team of astronomers using a project called Super WSP, which stands for Wide Angle Search for Planets. SUPERWA uses automated telescopes to monitor thousands of stars, looking for tiny dips in brightness that happen when a planet passes in front of its star, blocking a small amount of light. This is called the transit method, and it's one of the most successful ways to find exoplanets. When a planet transits its star, the star's brightness drops very slightly, usually by less than 1%. But if you measure the star's brightness very carefully over many nights, you can detect this dip. And by studying the pattern of dips, you can learn a lot about the planet, how big it is, how close it orbits, how long its year is, and sometimes even details about its atmosphere. WASP-12b orbits a star called WASP-12, located about 1,400 light-years away from Earth in the constellation Auriga. The star is a bit larger and hotter than our Sun, a yellow-white star that's been shining for a few billion years. And orbiting this star, at a distance of only 2.1 million miles, is WASP-12b. To put that distance in perspective, our moon is about 240,000 miles from Earth. WASP-12b is less than 9 times farther from its star than our moon is from Earth. Mercury, the closest planet to our Sun, is about 36 million miles away at its closest. WASP-12b is more than 15 times closer to its star than Mercury is to the Sun. It's practically skimming the star's surface. Because it's so close, WASP-12b orbits incredibly fast. Its year, the time it takes to complete one full orbit, is only 1.09 Earth days. That's right, just a little over 1 day. The planet is moving at about 150 miles per second, racing around its star at a speed that's hard to imagine. And because it's so close, the planet is hot, unbelievably hot. The side of the planet facing the star, called the day side, has a temperature of about 4,600 degrees Fahrenheit. That's hot enough to vaporize iron. It's hotter than some stars. The planet glows from its own heat, not just from reflected starlight, emitting infrared radiation like a hot coal. WASP-12b is also huge. It has about 1.4 times the mass of Jupiter, making it one of the more massive planets ever discovered. But here's something strange. Despite being more massive than Jupiter, it's much, much larger. Its radius is about 1.9 times Jupiter's radius. If Jupiter is the size of a basketball, WASP-12b is the size of a large beach ball. Why is it so bloated? The intense heat from its star is the answer. The heat pours into the planet's atmosphere, causing the gas to expand enormously. The atmosphere is puffed up, inflated to an extraordinary size. The planet's density is incredibly low, less than 1/10 the density of water. If you could find a bathtub big enough, WASP-12b would float. But the heat is doing more than just inflating the planet. It's destroying it. The temperature is so high that molecules in the atmosphere are being broken apart into individual atoms. Hydrogen molecules split into hydrogen atoms. Some atoms are being ionized, stripped of their electrons, creating a plasma. And the most disturbing part, the atmosphere is escaping into space. When astronomers studied WASP-12b's atmosphere using the Hubble Space Telescope, they discovered that the planet is surrounded by a huge cloud of gas. The atmosphere is literally boiling away, streaming off the planet into space. The star's intense ultraviolet radiation is heating the upper atmosphere to such extreme temperatures that the gas is no longer bound by the planet's gravity. It's escaping, flowing away from the planet in all directions. Scientists calculated that WASP-12b is losing about 6 billion tons of material every second. To give you a sense of scale, that's like losing a mountain the size of Mount Everest every few seconds. Over the course of a year, the planet loses about 0.0000003% of its total mass. That might sound tiny, but it adds up. Over 10 million years, the planet could lose about 0.3% of its mass. Over hundreds of millions of years, a significant fraction of the planet could simply evaporate away. But the atmospheric loss is only one of the problems WASP-12b faces. There's something even more dangerous happening, something that threatens to destroy the planet much faster than evaporation. That danger is tidal forces. You're probably familiar with tides on Earth. The moon's gravity pulls on the Earth, and because the moon is closer to one side of the Earth than the other, it pulls more strongly on the near side. This creates a bulge in the Earth's oceans, on the side facing the moon, and another bulge on the opposite side. These bulges are the tides, the regular rising and falling of sea levels that happens twice a day. Now imagine if the moon were much closer, so close that its gravity wasn't just pulling on the oceans, but on the solid Earth itself. The tidal forces would become extreme. The Earth would be stretched, deformed into an egg shape, with the long axis pointing toward and away from the moon. And as the Earth rotated, this stretching and squeezing would flex the planet's interior, generating enormous amounts of heat through friction. This is exactly what's happening to WASP-12b, except instead of the moon pulling on Earth, it's the star WASP-12 pulling on the planet. And because the star is so much more massive than the moon, and because WASP-12b is so much closer to its star than the moon is to Earth, the tidal forces are immense. WASP-12b is being stretched into an egg shape. Observations confirm this. The planet is not round. It's elongated, with the long axis pointing toward and away from the star. The difference between the planet's equatorial diameter and its polar diameter is enormous, much larger than for any planet in our solar system. And here's where things get really disturbing. The tidal forces are not just stretching the planet, they're pulling it apart. The gravity from the star is stronger on the side of the planet facing the star than on the far side. This difference in gravitational pull, called a tidal gradient, is trying to rip the planet apart. It's like pulling on opposite ends of a piece of taffy, stretching it until it breaks. For most planets, this wouldn't be a problem. The planet's own gravity holds it together, and the tidal forces from the star are too weak to overcome that. But WASP-12b is right on the edge. It's so close to its star that the tidal forces are almost as strong as the planet's self-gravity. The planet is being pulled in two directions at once, its own gravity trying to hold it together, and the star's tidal forces trying to tear it apart. Scientists have a name for the distance where tidal forces become strong enough to destroy an object: the Roche limit. If an object gets closer to a massive body than the Roche limit, tidal forces win and the object is torn apart. The Roche limit depends on the densities and sizes of the two objects. But for WASP-12b and its star, scientists calculated that the Roche limit is very close to where the planet actually is. In fact, some calculations suggested that WASP-12b might already be inside its Roche limit, or at least very close to it. If that's true, the planet should be disintegrating right now. It should be falling apart, with material streaming off it, forming a ring or a disk around the star. The planet might have only a few million years left before it's completely destroyed. When this analysis was published, it shocked the astronomy community. Here was a planet that we could observe, that we could study, that might be in its final death throes. We might be watching, in real time, the destruction of an entire world. It was both fascinating and disturbing. But there was a problem. As years passed and astronomers continued to observe WASP-12b, the planet was still there. It wasn't falling apart, at least not in any obvious way. Yes, it was losing its atmosphere. Yes, it was being stretched and heated. But it was surviving. It was holding together. And nobody could explain why. As astronomers studied WASP-12b more carefully, they discovered something even more alarming. The planet wasn't just sitting in a dangerous orbit. It was falling. Slowly, gradually, but unmistakably, WASP-12b was spiraling inward toward its star. Here's how they figured this out. When a planet transits its star, the exact time when the transit happens can be measured very precisely. If the planet's orbit is perfectly stable, the transits should happen like clockwork at exactly regular intervals. You can predict when the next transit will occur by simply adding the orbital period to the time of the last transit. But if the orbit is changing, if the planet is moving closer to or farther from the star, then the transits won't happen exactly when predicted. They'll occur a little bit early or a little bit late. By measuring the timing of many transits over several years, astronomers can detect tiny changes in the orbit. This technique is called transit timing, and it's incredibly sensitive. It can detect orbital changes as small as a few milliseconds per year. And when astronomers applied this technique to WASP, they found something disturbing. In 2017, a team of astronomers published a paper showing that the transits of WASP-12b were happening earlier than expected, not by much, just by about 30 milliseconds per year. But that tiny difference was statistically significant and growing over time. The simplest explanation was that the planet's orbital period was decreasing. The planet was orbiting faster, which meant it was moving closer to the star. The rate of orbital decay was measured at about 10 milliseconds per year. That means every year, the planet completes its orbit about 10 milliseconds faster than the year before. Over decades and centuries, this adds up. The planet is spiraling inward, following a death spiral that will eventually end with the planet plunging into its star. Why is this happening? The answer is tidal interactions, but in a more subtle way than we discussed before. When the star's tidal forces stretch the planet, they create bulges in the planet's shape. But the planet is also rotating, though not very fast because it's tidally locked, meaning the same side always faces the star, just like the moon is tidally locked to Earth. Because the planet has some internal friction, the tidal bulges don't line up exactly with the direction to the star. They're offset slightly. This offset means that the gravitational pull between the star and the bulges creates a torque, a twisting force. This torque acts like a brake, slowing down the planet's orbital motion. As the planet's orbital motion slows down, it loses angular momentum and energy. Where does that energy go? It gets converted into heat, both in the planet and in the star, through tidal friction. And as the planet loses energy, it falls into a lower orbit, closer to the star. This process is called orbital decay, and it's inevitable for any planet orbiting very close to its star. In our solar system, orbital decay is happening too, but very, very slowly. The moon is actually moving away from Earth, not closer, because of tidal interactions. But that's a special case related to the Earth-Moon system's specific properties. For planets very close to their stars, the usual outcome is that they spiral inward. For most hot Jupiters, orbital decay is so slow that it takes billions of years to have any noticeable effect. The planet was going to die anyway when its star evolved and swelled into a red giant, so the orbital decay doesn't really matter. But WSP-12b is different. Its orbital decay is fast, much faster than for other planets. Scientists calculated that, at the current rate of decay, WASP-12b will spiral into its star in about 3 million years. That might sound like a long time, but in astronomical terms, it's the blink of an eye. 3 million years ago on Earth, our human ancestors were just beginning to use stone tools. In cosmic terms, 3 million years is nothing. This added a new layer to the mystery. Not only is WASP-12b surviving when it shouldn't, but it's also doomed to fall into its star in the very near future. The planet is living on borrowed time, and the clock is ticking faster than anyone expected. But here's where things get even stranger. Some astronomers questioned the orbital decay measurements. They pointed out that measuring changes of 10 milliseconds per year is incredibly difficult. There are many sources of error and many other effects that could mimic orbital decay. For example, if the star itself is changing its brightness in ways we don't fully understand, that could affect the transit timing measurements. If there are other planets in the system that we haven't detected yet, their gravitational influence could perturb WASP-12b's orbit in complex ways. In 2019, another team of astronomers published a paper challenging the orbital decay result. They reanalyzed the transit timing data, including new observations, and they concluded that there was no convincing evidence of orbital decay. According to their analysis, the orbit was stable, at least within the measurement uncertainties. This created a controversy. Two different teams, looking at similar data, reached opposite conclusions. Who was right? Was WSP-12b spiraling to its doom? Or was it in a stable orbit? And if it was stable, why? What force was preventing the orbital decay that should be happening? The debate is still ongoing. More observations are being made, more data is being collected, and scientists are refining their analysis techniques. But the fact that we can't definitively answer this question is itself disturbing. We're observing a planet 1,400 light-years away, and we can't tell for sure whether it's falling into its star or not. The uncertainties in our measurements and our understanding are larger than we'd like to admit. What is clear is that WASP-12b is in a precarious situation. Whether it's currently decaying or not, it's in an orbit where tidal forces are enormous, where the planet is being stretched and heated, where the atmosphere is escaping, and where long-term stability is questionable. Something is wrong with this planet. Something doesn't add up, and scientists are determined to figure out what it is. Let's dive deeper into what tidal forces are actually doing to WASP-12b, because the more we look, the stranger it gets. We've talked about the planet being stretched into an egg shape, but the reality is even more extreme than that simple description suggests. When you stretch something, you're applying force to it, and that force creates stress inside the material. If the stress is too great, the material deforms, breaks, or flows. For a planet made mostly of gas, like WASP-12b, the response to tidal stress is different from what would happen to a solid object like Earth. WASP-12b doesn't have a solid surface. It's a giant ball of gas, mostly hydrogen and helium, with perhaps a small rocky or icy core deep in the center. The gas in the atmosphere and in the deep interior can flow, responding to the forces acting on it. When tidal forces stretch the planet, the gas flows toward and away from the star, creating the egg shape. But this flow is not simple. The planet is also rotating, though slowly because it's tidally locked. There are winds in the atmosphere, driven by the extreme temperature difference between the day side and night side. The star's radiation is constantly heating the day side atmosphere, causing it to expand and creating pressure differences that drive massive flows of gas around the planet. On the day side, where the temperature is 4,600 degrees Fahrenheit, the gas is so hot that hydrogen molecules are breaking apart into individual atoms. Some of these atoms are ionized, becoming plasma. The atmosphere on the day side is puffed up, expanded to enormous heights, extending far above the planet's nominal radius. On the night side, which doesn't receive direct starlight, the temperature drops, though not nearly as much as you might expect. The atmosphere transports heat from the day side to the night side through winds. Even so, the night side is cooler, and the atmosphere there is somewhat less expanded. This creates an asymmetry in the planet's shape. The day side bulge is larger than the night side bulge. The planet is not a simple ellipsoid, but a lumpy, irregular shape, constantly shifting as gas flows around it. Astronomers using the Hubble Space Telescope and other observatories have tried to map the shape of WASP-12b by observing how the planet blocks starlight during transit. The results confirm that the planet is significantly distorted. But there's more. The tidal forces are not just stretching the planet's atmosphere, they're also affecting the interior. Deep inside WASP-12b, beneath the outer atmosphere, there's a region where the pressure and temperature are so high that hydrogen behaves in strange ways. At those extreme conditions, hydrogen is no longer a gas. It becomes a liquid, and at even higher pressures, it becomes metallic, able to conduct electricity like a metal. This metallic hydrogen layer is thought to exist in all gas giant planets, including Jupiter and Saturn. It's incredibly difficult to study because we can't see inside planets, and we can't create metallic hydrogen in laboratories except under the most extreme conditions. But computer simulations based on the laws of physics suggest that metallic hydrogen should exist in the deep interiors of gas giants. In WASP-12b, the tidal forces are stretching and squeezing not just the atmosphere, but this deep interior as well. As the planet orbits its star, the tidal forces change direction and magnitude, causing the interior to flex. This flexing generates heat through friction, a process called tidal heating. Tidal heating is very effective in WASP-12b because the tidal forces are so strong. Some scientists estimate that tidal heating could be contributing as much energy to the planet as it receives from its star's radiation. This means the planet is being heated from the inside and the outside simultaneously. The heat from tidal friction is one reason why WASP-12b is so bloated. The internal heat source adds to the external heating from the star, causing the atmosphere to expand even more. The planet is like a balloon being heated with a blowtorch, while also being squeezed and stretched. It's a wonder the balloon doesn't pop. In fact, there are theories suggesting that WASP-12b might be on the verge of popping, or at least tearing open. If the tidal forces and internal heating become too extreme, parts of the atmosphere might escape not just through gradual evaporation, but through violent outbursts, like geysers erupting from the planet's atmosphere. Some models predict that the planet could have massive storms or eruptions on its day side, where the hottest gas breaks free from the planet's gravity and streams into space. Observations have detected spectral signatures, suggesting that the escaping gas is not uniformly distributed around the planet. There are hints of asymmetries, regions where more gas is escaping than others. This could be evidence of these violent processes, though the data is still too uncertain to say for sure. What's particularly disturbing is that all these processes feed back on each other. The tidal heating causes the atmosphere to expand, which makes the planet's radius larger, which makes the tidal forces stronger, because the star's gravity affects a larger volume of the planet. Stronger tidal forces mean more tidal heating, which causes more expansion, which increases tidal forces further. This is a runaway feedback loop, and it's not clear what stops it. In theory, there should be a balance. The planet heats up and expands until the rate of energy loss through radiation and atmospheric escape matches the rate of energy input from the star and tidal heating. At that point, the planet reaches an equilibrium and stops expanding. But WASP-12b might not be in equilibrium. It might still be adjusting, still changing, possibly even accelerating toward a catastrophic end. Some scientists have proposed that WASP-12b is in the process of transitioning from a gas giant to something else entirely. If the planet loses enough of its atmosphere, it might eventually be stripped down to its core, becoming a much smaller, denser object. This core might be rocky or icy, depending on what the planet's interior is made of. The result would be a hot, dense planet orbiting very close to its star, a type of planet we call a Chthonian planet, named after the Greek gods of the underworld. A few Chthonian planets have been detected, worlds that are probably the remnants of gas giants that lost their atmospheres. They're rare, or at least rare enough that we haven't found many, but they prove that the process of atmospheric stripping can go to completion. WASP-12b might be on its way to becoming one of these worlds, a naked planetary core exposed to the fury of its star. But there's a catch. If WASP-12b is losing its atmosphere and spiraling inward, and if these processes are happening on timescales of millions of years, then we're incredibly lucky to be observing it right now. The planet has been around for billions of years, and it will exist for at least a few million years more. The chance that we're observing it during this brief, dramatic phase of its life is tiny. This is called a selection bias problem. Are we just lucky, or is there something wrong with our understanding? Maybe the process is slower than we think. Maybe the planet is not as doomed as it appears. Maybe there's some mechanism we don't understand that's stabilizing the planet, preventing it from spiraling in, preventing its atmosphere from escaping as fast as we calculate. This brings us to the heart of the mystery. Why is WASP-12b still here? What's keeping it together? And if we're wrong about WASP-12b, what else are we wrong about? One idea that scientists have explored is that WASP-12b might have a magnetic field, and that magnetic field might be protecting the planet in ways we don't fully understand. Magnetic fields are common in planets and stars. Earth has a magnetic field generated by the motion of molten iron in its core. This field extends far into space, creating a protective bubble called the magnetosphere. The magnetosphere deflects most of the solar wind, the stream of charged particles from the sun, preventing them from stripping away our atmosphere. Gas giant planets like Jupiter also have magnetic fields, and Jupiter's is incredibly strong, the strongest of any planet in our solar system. The magnetic field is generated by the motion of metallic hydrogen in Jupiter's interior. The rotation of the planet causes the metallic hydrogen to swirl and flow, creating electric currents, and these currents generate the magnetic field. Does WASP-12b have a magnetic field? We don't know for sure. We can't directly measure the magnetic field of a planet 1,400 light-years away, but we can make educated guesses based on what we know about how magnetic fields are generated. For a planet to have a strong magnetic field, it needs three things. First, it needs a conducting fluid in its interior, like metallic hydrogen. WASP-12b probably has that. Second, it needs that fluid to be in motion, flowing and swirling. The interior of WASP-12b is being heated and stirred by tidal forces, so there's definitely motion. Third, the planet needs to be rotating fast enough for the Coriolis effect, organize the flows into patterns that generate a coherent magnetic field. This is where things get tricky. WASP-12b is tidally locked, meaning it rotates very slowly. It takes 1.09 days to complete one orbit, and it probably rotates once every 1.09 days as well, keeping the same face toward the star. This slow rotation might not be fast enough to generate a strong magnetic field through the usual dynamo process. On the other hand, the tidal heating and the extreme conditions in the planet's interior might create convection, large-scale flows of gas rising and falling as hot material rises and cool material sinks. These convection currents, if they're organized in the right way, could potentially generate a magnetic field even without fast rotation. Some computer models suggest this is possible, though others are skeptical. If WASP-12b does have a magnetic field, it could be protecting the planet in several ways. First, the magnetic field could deflect some of the high-energy particles from the star, reducing the rate at which the atmosphere is ionized and heated. This would slow down the atmospheric escape. Second, the magnetic field could help hold the atmosphere together. A magnetic field exerts a force on charged particles, essentially creating a cage that keeps ionized gas from escaping too easily. This is similar to how Earth's magnetosphere helps protect our atmosphere. Third, the magnetic field could interact with the star's magnetic field in complex ways. Both the star and the planet are rotating and have magnetic fields, and these fields can link up, creating magnetic loops that connect the star and the planet. This phenomenon is called magnetic reconnection, and it releases enormous amounts of energy in the form of flares and particle jets. Some scientists have suggested that magnetic reconnection between WASP-12 and WASP-12b could be transferring angular momentum from the star to the planet, essentially giving the planet a boost that counteracts the orbital decay caused by tidal friction. This would be like a gravitational tug-of-war, with tidal forces pulling the planet inward and magnetic forces pushing it outward, and the two effects balancing each other out. This is a speculative idea, and there's no direct evidence for it yet. But it's the kind of idea that gets scientists excited because it offers a way to explain why WASP-12b is surviving when it shouldn't. If magnetic interactions are keeping the planet in a stable orbit, then the planet isn't doomed after all. It's being protected by invisible forces, a magnetic lifeline connecting it to its star. To test this idea, astronomers are looking for signs of magnetic activity around WASP-12b. One thing they're searching for is auroras. On Earth, auroras are the northern and southern lights, caused by charged particles from the solar wind colliding with atoms in our upper atmosphere, making them glow. The particles are guided by Earth's magnetic field toward the poles, which is why auroras appear near the Arctic and Antarctic. Gas giant planets in our solar system, like Jupiter and Saturn, also have auroras, much more powerful than Earth's. Jupiter's auroras are so bright that they emit X-rays and radio waves that we can detect from Earth. If WASP-12b has a strong magnetic field and is being bombarded by particles from its star. It might have auroras too, potentially visible with our telescopes. Astronomers have searched for X-rays and radio waves from WASP-12b using space-based X-ray telescopes and radio telescopes on Earth. So far, the results are inconclusive. Some observations hint at possible emission, but the signals are weak and difficult to distinguish from noise and from emission from the star itself. Another approach is to look at the spectrum of light from WASP-12b's atmosphere. When charged particles collide with atoms, they can excite those atoms, causing them to emit light at specific wavelengths. By searching for these emission lines in the planet's spectrum, astronomers can potentially detect auroral activity. The Hubble Space Telescope and other instruments have taken spectra of WASP-12b during transit. When the planet passes in front of its star, the starlight filters through the planet's atmosphere, and by comparing the spectrum during transit to the spectrum when the planet is not transiting, astronomers can figure out what the atmosphere is made of and what processes are happening there. These observations have detected hydrogen, helium, sodium, and other elements in the atmosphere. They've also found evidence of molecules being broken apart and of gas escaping from the planet. But so far, there's no clear detection of auroral emission. This doesn't mean there are no auroras, just that if they exist, they're either too faint to see or they're happening at wavelengths we haven't observed yet. The magnetic field hypothesis remains an intriguing possibility, but not a proven fact. We need more data, better observations, and probably new instruments that can detect faint signals from faraway planets. The James Webb Space Telescope, which launched in 2021 and began operations in 2022, is much more sensitive than Hubble and can observe at infrared wavelengths, where some of these signals might be stronger. Scientists are using JWST to study WASP-12b, and the results could finally tell us whether the planet has a magnetic field and what role it plays in the planet's survival. Another possibility that scientists have considered is that WASP-12b might not be alone. There might be another planet in the system, a companion that we haven't detected yet, and this companion's gravity could be affecting WASP-12b in ways that explain some of the mysteries. Detecting planets is hard, especially if they're small or if they orbit far from their star. The methods we use to find planets, like the radial velocity technique and the transit method, work best for large planets orbiting close to their stars. A small planet, or a planet in a distant orbit, produces much weaker signals and is easy to miss. So it's entirely possible that there are other planets orbiting WASP-12 that we don't know about. And if there are, their gravitational influence could be perturbing WASP-12b's orbit. Gravitational interactions between planets can do strange things. Planets can nudge each other into different orbits, speed each other up or slow each other down, change the shape of each other's orbits, or even fling each other out of the system entirely. One scenario is that there's a second planet farther out from the star, and this planet's gravity is pulling on WASP-12b in a periodic way. This could create variations in WASP-12 WASP-12b's orbit that look like orbital decay, but aren't. The orbit might be stable on average, but the gravitational tug from the companion causes the orbit to vary slightly over time, making the transits happen a little early or a little late in a pattern that repeats. This kind of effect is called a perturbation, and it's a well-known phenomenon in celestial mechanics. The planets in our solar system perturb each other's orbits all the time. For example, Jupiter's gravity perturbs the orbits of the inner planets slightly. These perturbations are tiny, but over long periods of time, they can add up and have noticeable effects. If there's a companion planet in the WASP-12 system, it could also affect WASP-12b's survival in more direct ways. For example, the companion's gravity could be pumping energy into WASP-12b's orbit through a process called resonance. This happens when two planets' orbital periods are related by a simple ratio, like 2 to 1 or 3 to 2. When planets are in resonance, their gravitational interactions repeat in a regular pattern, and this can transfer energy between the planets. If energy is being added to WASP-12b's orbit by a resonance interaction, that could counteract the energy loss from tidal friction, keeping the planet from spiraling inward. The planet would be in a kind of gravitational balance, with two opposing processes canceling each other out. To search for companion planets, astronomers analyze the timing of WASP-12b's transits very carefully, looking for periodic variations that would indicate the presence of another planet. They also look at the radial velocity data, the measurements of the star's wobble, to see if there are additional wobbles caused by other planets. So far, no convincing evidence of a companion planet has been found. The transit timing variations that have been observed don't match the pattern you'd expect from a simple companion. The radial velocity data is noisy and doesn't clearly show additional planets, but that doesn't mean there's nothing there. A small planet, or a planet in just the wrong orbit, might produce signals too subtle to detect with current data. Astronomers are continuing to monitor WASP-12, collecting more observations over more years, hoping that with enough data, the pattern will become clear. If there is a companion planet, eventually its influence will reveal itself. And if there isn't, then we can rule out that explanation and focus on others. There's also the possibility of something even more exotic, a companion that isn't a planet at all, but a brown dwarf or even a small star. Brown dwarfs are objects that are more massive than planets, but not massive enough to ignite nuclear fusion in their cores like stars do. They're sometimes called failed stars. A brown dwarf companion orbiting WASP-12 at a distance could exert gravitational influence on WASP-12b. If such a companion existed, it should be detectable with infrared telescopes because brown dwarfs emit their own heat. Astronomers have looked, and they haven't found any brown dwarf companions close enough to affect WASP-12b. But again, that doesn't completely rule out the possibility. A very faint brown dwarf or a companion in just the right orbit to hide from our observations could still be there. The search for hidden companions is ongoing, and it's one piece of the larger puzzle. Every possibility has to be explored, every hypothesis tested, until we either find the answer or run out of ideas. Let's turn our attention to what's happening in WASP-12b's atmosphere, because the more scientists study it, the more bizarre it becomes. The atmosphere is not just hot. It's being actively destroyed, stripped away into space, and the rate at which this is happening is alarming. When atoms or molecules in an atmosphere are heated to very high temperatures, they move faster. If they move fast enough, they can escape the planet's gravity and fly off into space. The speed needed to escape is called the escape velocity, and it depends on the planet's mass and radius. For Earth, the escape velocity is about 7 miles per second. For a massive planet like WASP-12b, it's higher, but not by as much as you might think, because the planet is so bloated that its surface gravity is actually quite low. On the day side of WASP-12b, the temperature is so high that hydrogen atoms are moving at speeds close to the escape velocity. The star's ultraviolet radiation hits the upper atmosphere and ionizes the atoms, stripping away electrons and creating ions. These ions are heated even further by absorbing more radiation, and eventually, some of them reach escape velocity and fly off into space. But atmospheric escape is not just a matter of atoms randomly flying away. There are organized flows, winds that carry gas from the planet into space. These flows are driven by pressure differences in the atmosphere. The day side is heated by the star, so the pressure there is high. The night side is cooler, so the pressure is lower. Gas naturally flows from high pressure to low pressure, creating winds that circle the planet. At the top of the atmosphere, on the day side, the pressure gradient is so extreme that gas is pushed outward, away from the planet, into space. This creates a kind of atmospheric wind that's blowing off the planet, carrying atoms and molecules with it. Scientists call this a hydrodynamic outflow, and it's like a river of gas flowing from the planet into the surrounding space. Observations with the Hubble Space Telescope have detected this outflow directly. Hubble observed WASP-12b in ultraviolet light, looking at the spectrum of the star's light as it filters through the planet's atmosphere. During transit, the planet's atmosphere absorbs some of the star's ultraviolet light, creating absorption lines in the spectrum. By studying these lines, astronomers can tell what the atmosphere is made of and how fast it's moving. What they found was stunning. The absorption lines were shifted in wavelength, indicating that the gas was moving at high speeds, up to 120,000 miles per hour. This is much faster than you'd expect from the planet's rotation or from normal atmospheric winds. The only explanation is that the gas is escaping, flowing away from the planet into space. Even more disturbing, the absorption was detected not just during the transit, when the planet is directly in front of the star, but also before and after the transit. This means the escaping gas extends far beyond the planet's actual size. The planet is surrounded by a huge cloud of gas, a kind of extended atmosphere or exosphere that's being blown off into space by the star's radiation. The size of this cloud is enormous. It extends to several times the planet's radius, creating a halo around the planet. If you could see WASP-12b up close, you wouldn't see a sharp edge to the planet. Instead, you'd see a fuzzy ball of glowing gas, gradually thinning out as you move away from the center, with streamers of gas flowing away from the planet like hair blowing in the wind. Scientists estimate that WASP-12b is losing about 6 billion tons of gas every second. To put that in perspective, that's about 200 billion tons per year. Over the lifetime of the planet, if this rate has been constant, the planet could have lost a significant fraction of its original mass. But here's a puzzle. If WASP-12b has been losing gas at this rate for its entire history, which could be billions of years, then by now the planet should have lost much more mass than it currently has. Either the planet started out much more massive than it is now, or the escape rate has not been constant. One possibility is that the escape rate has increased over time. As the planet loses mass, it becomes less massive and its gravity weakens. Weaker gravity means the escape velocity decreases, making it easier for gas to escape. This creates a feedback loop. As the planet loses gas, it becomes easier to lose more gas, and the escape rate accelerates. Another possibility is that the planet hasn't been in its current orbit for billions of years. Maybe it migrated inward more recently, and the extreme atmospheric loss only started when it got close enough to its star for the heat and radiation to become intense. If the planet has only been in this orbit for, say, tens or hundreds of millions of years, then the total mass loss would be much less, and the numbers would add up better. But both of these possibilities have problems. If the escape rate is accelerating, the planet is doomed even faster than we thought. And if the planet only recently migrated inward, we're even more lucky to be observing it right now, which brings us back to the selection bias problem. There's another aspect of the atmospheric escape that's deeply strange. The gas that's escaping is not just hydrogen. Observations have detected heavier elements like carbon and oxygen in the outflow. This is surprising because heavier elements are harder to escape because they're more strongly bound by gravity. For them to be escaping, they must be getting swept up in the flow of hydrogen, carried along like dust in a river. This tells us that the outflow is very powerful, strong enough to drag heavy atoms with it. It also tells us that the composition of the planet is changing. As the light hydrogen escapes faster than the heavy elements, the planet's atmosphere becomes enriched in heavier elements. Over time, this could change the planet's properties in significant ways. Some scientists have speculated that WASP-12b might eventually lose all of its hydrogen atmosphere, leaving behind a core made of heavier elements, possibly even a solid surface made of carbon or silicates. This core might then continue to lose material, but at a slower rate, until it's eventually stripped down to nothing, or until it falls into the star. The James Webb Space Telescope has been observing WASP-12b to study its atmosphere in even greater detail. JWST can observe at infrared wavelengths, which are particularly good for detecting molecules and measuring temperatures. The observations are revealing the composition of the atmosphere, the temperature structure, and how energy flows from the day side to the night side. Early results from JWST confirm that the atmosphere is incredibly hot and that water molecules, which should be present in a hydrogen-rich atmosphere, are almost completely absent on the day side. They're being broken apart by the intense heat and radiation. On the night side, there might be some water vapor, but even there, the conditions are harsh. JWST has also detected carbon monoxide and possibly other carbon-bearing molecules. Carbon is an important element for understanding the planet's formation and evolution because it's abundant in the universe and plays a key role in chemistry. The amount of carbon in the atmosphere and the ratio of carbon to oxygen can tell us about the planet's history and where it formed. All of this data is painting a picture of a planet in extreme distress, a world being torn apart by forces it cannot resist. And yet, as we've said, the planet is still there. It's surviving, at least for now. And that survival is what makes WSP-12b so important and so mysterious. So far, we've focused on the planet, but the star WSP-12 has its own secrets, and they might be part of the reason why WSP-12b is in such a strange state. WSP-12 is not a typical Sun-like star. It's a bit larger, a bit more massive, and significantly hotter than the Sun. Its spectral type is F9, which means it's a yellow-white star. The Sun, by comparison, is a G2 star. This difference in spectral type translates to a difference in temperature. WAC-12's surface temperature is about 6,300 degrees Kelvin, compared to the Sun's 5,800 Kelvin. That might not sound like much, but it makes a significant difference in the star's energy output. WASP-12 is also older than the Sun. Its age is estimated to be between 2 and 3 billion years, while the Sun is about 4.6 billion years old. Wait, that doesn't sound older. Let me correct that. Actually, determining the exact age of stars is difficult, and different methods give different results. Some estimates place WASP-12 at around 2 billion years, which would make it younger than the Sun. Other estimates suggest it could be older. The uncertainty comes from difficulties in modeling the star's evolution, and from the fact that the star's rotation and magnetic activity have been affected by the close-in planet. One of the interesting things about WASP-12 is that it's metal-rich. In astronomy, metals means any element heavier than hydrogen and helium. So carbon, oxygen, iron, and all the others are called metals, even though they're not metals in the chemistry sense. Stars that are metal-rich have higher abundances of these heavy elements, usually because they formed from gas clouds that were already enriched by previous generations of stars. Why is WASP-12 metal-rich? There are several possibilities. One is that it simply formed from a metal-rich cloud. Another, more intriguing possibility is that the star has been polluted by material from its planet. Remember that WASP-12b is losing 6 billion tons of gas every second. That gas doesn't just disappear into space. Some of it falls onto the star, raining down onto the star's surface and adding to its mass. If WASP-12b has been losing gas for a long time, a significant amount of material could have been transferred to the star. This material would be rich in heavy elements because, as we discussed, the heavier elements are less likely to escape and get left behind in the escaping gas. Over time, this could enrich the star's atmosphere with metals. Some scientists have looked for evidence of this pollution by studying the star's spectrum in detail, looking for unusual abundances of certain elements. The results are inconclusive. There are some hints of unusual abundances, but it's hard to say for sure whether they're due to pollution from the planet or just natural variations. Another peculiar feature of WASP-12 is that it seems to be spinning faster than expected. Stars slow down their rotation over time due to magnetic braking, a process where the star's magnetic field interacts with the stellar wind and transfers angular momentum away from the star. Older stars should be rotating slowly, but WASP-12 is rotating faster than you'd expect for its age. Why? One possibility is that the star has been spun up by interactions with the planet. When a planet orbits very close to a star, tidal forces affect both the planet and the star. The planet can transfer some of its orbital angular momentum to the star, causing the star to spin faster. This is the opposite of the effect that causes the planet's orbit to decay. If WASP-12 has been spun up by its planet, that's evidence of strong tidal interactions, which supports the idea that WASP-12b is in a precarious orbit and that the star and planet are locked in a gravitational dance that's changing both of them over time. There's also the star's magnetic activity to consider. Stars have magnetic fields generated by dynamos in their interiors, similar to planets. These magnetic fields can create spots on the star's surface called star spots, which are darker and cooler than the surrounding areas. They're similar to sunspots on our sun. Magnetic fields can also cause flares, sudden releases of energy that brighten the star temporarily. WASP-12 shows signs of magnetic activity, including variability in its brightness, that could be due to star spots rotating in and out of view. This activity could be affecting the measurements of the planet's transits, creating noise in the data that makes it harder to detect subtle effects like orbital decay. More disturbingly, magnetic activity could be affecting the planet directly. Flares from the star release bursts of high-energy radiation and particles. And if these hit the planet, they could strip away even more of its atmosphere. The planet is already in a harsh environment, and flares would make things even worse. Some scientists have suggested that we might be observing WAC-12b during a particularly active phase of the star's life, when magnetic activity is high and the planet is under more stress than usual. This could explain why the planet seems to be losing its atmosphere so fast. If the star calms down in the future, the planet's escape rate might decrease, giving it a longer lifetime. But this is speculative. We don't know enough about how stars like WASP-12 vary over time, or how their activity affects their planets. This is an area of active research and new observations, especially from missions like TESS, Transiting Exoplanet Survey Satellite, and from JWST, are helping to fill in the gaps in our understanding. The star WAC-12 is not just a passive light source. It's an active participant in the drama playing out in this system. The star's properties, its temperature, its magnetic field, its evolution, they all affect the planet and contribute to the mystery of why WASP-12b is still there when it shouldn't be. When astronomers encounter a mystery like WASP-12b, they don't just observe. They also run computer simulations, building models of the planet and the star, and letting the laws of physics play out to see what happens. These simulations are incredibly complex, involving calculations of gravity, heat flow, gas dynamics, magnetic fields, radiation, and more. The goal is to create a virtual version of WASP-12b, input all the known properties of the planet and star, and then run the simulation forward in time to see what the model predicts. If the model matches the observations, great. If it doesn't, that tells you something is wrong with your assumptions, and you need to adjust the model. For WASP-12b, scientists have built many models, and the results have been both enlightening and frustrating. Some models predict that the planet should be rapidly losing its atmosphere and spiraling into the star, exactly what observations seem to suggest. Other models predict that the planet should be more stable, that the tidal forces shouldn't be strong enough to destroy it, at least not yet. The differences between models come down to assumptions about things we don't know for sure. What is the internal structure of the planet? How much of it is hydrogen gas? And how much is rock or ice? How is heat transported through the interior? Does the planet have a strong magnetic field? How efficient is the tidal heating? Each of these questions has a range of possible answers, and different answers lead to different predictions. Scientists try to narrow down the possibilities by comparing model predictions to observations, but the observations have uncertainties too, and sometimes the observations are contradictory. One of the key uncertainties is the tidal dissipation factor, often called Q. This is a number that describes how efficiently tidal energy is converted into heat inside the planet. A low Q means efficient conversion, lots of tidal heating and rapid orbital decay. A high Q means inefficient conversion, less heating, and slower decay. For planets in our solar system, we can measure Q by observing how their orbits change over time. For Jupiter's moon Io, which is heated by tidal forces from Jupiter, we know Q fairly well. But for exoplanets like WASP-12b, we can't measure Q directly. We have to infer it from models, and different models give different values. Some models of WASP-12b use a low Q, consistent with what we see in Io, and these models predict rapid tidal heating and orbital decay. The planet should be spiraling into the star quickly and should be losing its atmosphere at a high rate. Other models use a higher Q, arguing that gas giants might dissipate tidal energy less efficiently than rocky moons, and these models predict slower decay and longer lifetimes. Which is right? We don't know. The observations of WASP-12b's orbital decay are disputed, as we discussed earlier, so we can't use them to definitively pin down Q. And without knowing Q, we can't make precise predictions about the planet's future. Another major uncertainty is the planet's interior structure. Is WASP-12b mostly gas all the way to the center, or does it have a significant core made of rock and ice? The mass of the core affects the planet's radius, its density, and how it responds to tidal forces. A large core would make the planet denser and less puffy, and it would change the distribution of mass inside the planet, affecting the tidal interactions. Observations can't directly tell us what's inside WASP-12b. We can measure the planet's total mass and radius, but the interior structure is hidden from view. We have to rely on models of planetary formation and evolution to make educated guesses. These models suggest that gas giants like WASP-12b probably have cores with masses between 10 and 100 times the mass of Earth, but the exact value is highly uncertain. Different core masses lead to different evolutionary paths for the planet. A planet with a large core might be more resistant to tidal disruption because the core's self-gravity helps hold it together. A planet with a small core might be more vulnerable because it's mostly gas, which can flow and be stripped away more easily. Scientists have run simulations with different core masses, different Q values, different assumptions about the star's properties, and different models of atmospheric escape. The result is a wide range of predictions, from planets that are destroyed in a few million years to planets that survive for 1 billion years or more. This range of outcomes is frustrating, but it's also a reflection of how much we still don't know. Planetary science is a young field, and exoplanet science even younger. We've only been studying planets around other stars for a few decades, and we're still learning the basics. Every new discovery, every new observation teaches us something and raises new questions. What the models do agree on is that WASP-12b is in an extreme environment, that it's being subjected to forces that are rare and intense, and that it's probably not in a stable, long-term equilibrium. Whether it's doomed to fall into its star, or whether it will find a way to survive, the planet is clearly in a transitional state, and we're lucky to be observing it. One of the most interesting predictions from the models is that WASP-12b's fate might depend on small, random factors. For example, if the planet's orbit is slightly elliptical rather than perfectly circular, that would increase the tidal heating, because the tidal forces would vary more as the planet moves closer to and farther from the star during each orbit. A small eccentricity could make the difference between survival and destruction. Observations suggest that WASP-12b's orbit is nearly circular, but there's a small measured eccentricity that might be real or might be an artifact of measurement errors. If it's real, it could be significant. If it's not real, then the planet's orbit is perfectly circular, and the tidal heating is less than it could be. Another factor is the planet's obliquity, the tilt of its rotation axis relative to its orbital plane. Earth's obliquity is 23.5 degrees, which is why we have seasons. If WASP-12b has a significant obliquity, it would affect how tidal forces act on the planet and how heat is distributed in the atmosphere. But again, we don't know what the obliquity is. We assume the planet is tidally locked with zero obliquity, but that might not be true. All of these uncertainties mean that we can't predict WASP-12b's future with confidence. The models give us possibilities, scenarios, ranges of outcomes, but they don't give us a definitive answer. And until we have better observations, better data, and a deeper understanding of the physics, we're stuck with uncertainty. This is the nature of science at the frontier. We push the boundaries of what we can observe and what we can understand, and we encounter mysteries that resist easy explanation. WASP-12b is one of those mysteries, a planet that should be falling apart, but isn't, or at least not as fast as we think it should. WASP-12b is not the only planet that's defying our expectations. As astronomers have discovered more and more exoplanets, they've found several other worlds that are in similarly precarious situations. By studying these planets, scientists hope to learn general lessons about how planets behave in extreme environments and why some survive when they shouldn't. One example is KELT-9b, which holds the record as the hottest exoplanet ever discovered. KELT-9b orbits a massive hot star, and its dayside temperature is an astonishing 7,800 degrees Fahrenheit. That's hotter than many stars. At this temperature, molecules can't exist. Even atoms are being ionized and broken apart. The planet's atmosphere is essentially a plasma, a soup of ions and free electrons. KELT-9b is also very close to its star, orbiting in just 1.5 days. And like WASP-12b, it's being bombarded with intense radiation and is losing its atmosphere. Observations have detected hydrogen, iron, and other elements streaming away from the planet. Scientists estimate that KELT-9b might be losing even more mass than WASP-12b, possibly tens of billions of tons per second. And yet, KELT-9b is still there. It's survived for however long it's been in this orbit, which could be millions or even billions of years. How? Nobody knows. The same questions that apply to WASP-12b apply to KELT-9b. Is there a magnetic field protecting it? Is it in a lucky orbit that allows it to survive? Is our understanding of atmospheric escape wrong? Another example is WASP-19b, a planet that's even closer to its star than WASP-12b. WASP-19b orbits in just 0.78 days, less than 19 hours. The planet is so close that the tidal forces are even more extreme than for WASP-12b, and the planet is stretched into an elongated shape. Observations confirm that the planet is highly inflated, with a radius more than twice Jupiter's, despite having only slightly more mass. WASP-19b should be losing its atmosphere rapidly and should be spiraling into its star. Some studies have claimed to detect orbital decay, while others dispute it, similar to the situation with WASP-12b. The planet remains a mystery, a world that's teetering on the edge of destruction, but somehow holding on. Then there's Kepler-1658b, a planet that's unique because it was one of the first planet candidates discovered by the Kepler Space Telescope, but it was initially classified as a false positive and dismissed. Years later, astronomers re-examined the data and realized it was a real planet after all. And it turned out to be a planet that's spiraling into its star. Kepler 1658b is a hot Jupiter orbiting a Sun-like star, and it's very close, completing an orbit in just 3.8 days. What makes Kepler 1658b special is that its orbital decay has been measured with high confidence. The planet's orbital period is decreasing by about 131 milliseconds per year, which is much faster than WASP 12b's disputed 10 milliseconds per year. This makes Kepler 1658b the first exoplanet where orbital decay has been definitively detected. The planet will spiral into its star in about 2.5 million years, making it doomed by astronomical standards. But it also provides a test case for theories of tidal interactions. By studying Kepler 1658b, scientists can measure the tidal dissipation factor and understand how efficiently energy is transferred between the star and planet. Another fascinating case is TOI 2109b, discovered by NASA's TESS mission. TOI 2109b is an ultra-hot Jupiter with a dayside temperature over 6,000 degrees Fahrenheit. It orbits its star in just 16 hours, making it one of the shortest orbital periods ever observed for a planet. The planet is incredibly close, almost skimming the star's surface. TOI 2109b is also showing signs of extremely rapid atmospheric escape. The star's intense radiation is stripping away the planet's atmosphere at a rate that might be even higher than WASP 12b. And because the orbit is so tight, the tidal forces are enormous. The planet is almost certainly doomed, destined to spiral into its star within a few million years. But again, it's still there. We're observing it now, which means it's survived long enough for us to find it. And that survival, however temporary, tells us something about the physics of planetary destruction. These planets are living on the absolute edge in the most extreme environments we know of, and they're teaching us about the limits of planetary existence. By comparing these different planets, scientists are starting to see patterns. Planets that are very close to very hot stars tend to be the most inflated and the most vulnerable to atmospheric escape. Planets around cooler stars, even if they're close, are less endangered. The star's radiation and magnetic activity play a huge role in determining the planet's fate. There are also hints that planetary migration might not always be a one-way trip. Some models suggest that under certain conditions, a planet that's spiraling inward could reverse course and start migrating outward again. This could happen if the star's magnetic field interacts with the planet in just the right way, or if there are other planets in the system that provide gravitational assists. If this is true, then planets like WASP 12b might be in dynamic orbits that oscillate over time, moving inward and outward, with their fate determined by a complex dance of competing forces. This would explain why we see planets in these extreme orbits at all. They're not permanently there. They're passing through, caught in a transitional phase that might last for millions of years before the planet either falls into the star or moves to a more stable orbit. This is speculative, and the evidence is limited, but it's an intriguing idea. It suggests that the universe of exoplanets is even more dynamic and chaotic than we thought, with planets constantly moving, changing, evolving in ways we're only beginning to understand. The existence of planets like WASP-12b has forced scientists to rethink their theories of how planets form and evolve. Before we started discovering exoplanets, our theories were based entirely on our solar system. And our solar system, as it turns out, is not a good model for planetary systems in general. In our solar system, the planets formed from a disk of gas and dust that surrounded the young sun. The inner part of the disk was hot, so only materials with high melting points, like rock and metal, could condense into solid particles. These particles stuck together to form the rocky planets: Mercury, Venus, Earth, and Mars. The outer part of the disk was cold, so ice could form, and there was more material available. This allowed the giant planets Jupiter, Saturn, Uranus, and Neptune to grow much larger by accumulating both ice and gas. Once the planets formed, they stayed mostly in the same orbits. There was some migration, especially for Jupiter and Saturn, which might have moved around a bit in the early solar system, causing chaos among the smaller bodies. But overall, the architecture of the solar system has been stable for billions of years. Hot Jupiters like WASP-12b don't fit this picture. Gas giants can't form close to their stars, where it's too hot for ice and gas to accumulate. So they must have formed farther out and then migrated inward. But how? One mechanism is called disk migration. When a young planet is still embedded in the disk of gas from which it formed, the planet's gravity creates spiral waves in the disk. These waves exert forces on the planet, and depending on the details, these forces can cause the planet to move either inward or outward. For most conditions, the net effect is that the planet spirals inward toward the star. As the planet migrates inward, it grows by accreting more gas from the disk. If the migration is slow enough, the planet can become very massive, possibly even more massive than Jupiter, before it gets too close to the star. Eventually, the disk dissipates, blown away by the star's radiation, or consumed by the growing planets, and the migration stops. The planet is left in whatever orbit it reached by the time the disk disappeared. If the planet migrated far enough inward, it ends up as a hot Jupiter, very close to its star. If it didn't migrate as far, it ends up in a more distant orbit. This explains why we see a range of orbital distances for giant planets, from ultra-hot Jupiters that orbit in hours to warm or cool Jupiters that orbit in weeks, months, or even years. But there's another migration mechanism that can be even more dramatic: gravitational scattering. If a planetary system has multiple giant planets, they can gravitationally interact with each other, pulling and pushing in a chaotic dance. Sometimes these interactions can fling one planet into a highly elliptical orbit, sending it careening toward the star at one end and far out into space at the other. When a planet on such an eccentric orbit comes close to the star, tidal forces act on it, circularizing the orbit over time. The planet gives up energy and angular momentum, and the orbit becomes rounder. Eventually, the planet ends up in a tight, circular orbit close to the star, a hot Jupiter. This scattering mechanism can also eject planets entirely, sending them flying out of the system into interstellar space. These rogue planets, drifting through the galaxy with no star, have been detected, and they're evidence that planetary systems can be violent, chaotic places where not every planet survives. Both disk migration and gravitational scattering probably happen, and different hot Jupiters probably formed through different paths. Some might have migrated gently through the disk, while others were thrown into their orbits by violent interactions with other planets. WSP-12b, with its extreme proximity to its star and its precarious state, might be a planet that didn't quite finish its migration. Maybe it was on its way to falling into the star, but got stalled somehow. Maybe the disk dissipated before the migration was complete, leaving the planet in a dangerous orbit that it's been stuck in ever since. Or maybe WASP-12b is a planet that was scattered into a highly eccentric orbit and is still in the process of circularizing. If that's the case, the orbit might be slowly evolving even now, which could explain some of the strange observations. Understanding planet formation is critical, not just for understanding exoplanets, but also for understanding our own solar system and for assessing the likelihood of finding Earth-like planets that might harbor life. If planetary systems are chaotic and planets can end up in all sorts of bizarre orbits, then finding a nice, stable, Earth-like planet in a comfortable orbit around a sun-like star might be much rarer than we hoped. On the other hand, the sheer diversity of exoplanets we've discovered suggests that planet formation is robust and can produce worlds under a wide range of conditions. Even if Earth-like planets are rare, there might be other types of habitable worlds, like moons of gas giants or planets around smaller, cooler stars, where life could arise. WSP-12b is a cautionary tale, a reminder that planets are not permanent, that they can be destroyed, and that the universe is a dangerous place. But it's also a testament to the creativity of nature, to the fact that planets can exist in environments that seem impossible, and that there's always more to learn, more to discover, more mysteries waiting to be solved. What will happen to WASP-12b in the future? Will it survive, or is it doomed to fall into its star? The honest answer is that we don't know, and we might not know for a long time. But we can make some educated guesses based on what we've learned. If WASP-12b is indeed spiraling inward, as some observations suggest, then its fate is sealed. The planet will continue to lose altitude, moving closer and closer to its star, until eventually it crosses the Roche limit and is torn apart by tidal forces. The timescale for this depends on the rate of orbital decay, but estimates range from a few 100,000 years to a few million years. As the planet approaches its doom, the tidal forces will become stronger, the tidal heating will increase, and the atmospheric escape will accelerate. The planet might start to break apart before it reaches the Roche limit, with chunks of gas and possibly even pieces of the core being stripped away and spiraling into the star. Eventually, there will be nothing left but a diffuse cloud of gas orbiting the star, and even that will dissipate over time, absorbed by the star or blown away by stellar winds. The star WASP-12 will continue shining, slightly enriched in heavy elements from the planet it consumed, but otherwise unchanged. It will be as if the planet never existed. This scenario is bleak, but it's consistent with what we know about tidal interactions and orbital decay. Many scientists think this is the most likely outcome for WASP-12b, though the timescale is uncertain. But there's another possibility. Maybe WASP-12b is not doomed. Maybe the orbital decay measurements are wrong. Or maybe there's a stabilizing mechanism we don't understand. If the planet has a strong magnetic field that's transferring angular momentum from the star, or if there's a hidden companion planet providing gravitational support, then WASP-12b might survive for much longer, perhaps for the entire remaining lifetime of its star. In that case, the planet would continue to lose its atmosphere, but slowly enough that it would take billions of years to lose a significant fraction of its mass. Eventually, the planet might be stripped down to its core, becoming a small, dense world, a remnant of its former self. This core might survive indefinitely, orbiting the star as a silent monument to the planet that once was. There's also the possibility that something traumatic will happen, a sudden event that changes everything. For example, the star WASP-12 will eventually evolve. In a few billion years, it will exhaust the hydrogen in its core and begin to expand into a red giant. As the star expands, it will engulf any close-in planets, including WASP-12b, if it's still there. But before that happens, the star's evolution might cause changes in its magnetic field, its rotation, its mass loss, all of which could affect the planet. The planet's orbit might change in response, moving inward faster or even moving outward if the star loses enough mass. The final fate of WASP-12b might be determined not by its current properties, but by what happens to the star in the future. From a human perspective, none of this matters much. WASP-12b is 1,400 light-years away, and whatever happens to it will have no effect on Earth. But from a scientific perspective, it matters enormously. WASP-12b is a laboratory, a place where we can study physics under extreme conditions that we can never recreate on Earth. By watching this planet, we learn about tidal forces, atmospheric escape, planetary interiors, magnetic fields, and the limits of planetary survival. Every observation of WASP-12b, every new measurement, every refinement of our models, brings us closer to understanding not just this one planet, but planets in general, including our own Earth. How stable is Earth's orbit? How long will our planet survive? What would happen if Earth were moved closer to the Sun, or if the Sun evolved differently? These are not idle questions. Understanding the long-term stability of planetary systems is important for understanding the history of life on Earth and the future of our planet. And while Earth is in no immediate danger, the study of planets like WASP-12b reminds us that the universe is dynamic, that change is inevitable, and that even planets have lifetimes. Scientists will continue to observe WASP-12b with every available tool. The James Webb Space Telescope will study its atmosphere in unprecedented detail. Future missions, like the European Space Agency's Ariel telescope, which will launch in the 2030s and is designed to study exoplanet atmospheres, will observe WASP-12b and dozens of other hot Jupiters, comparing them to understand the diversity of these worlds. Ground-based telescopes will continue to monitor the planet's transits, looking for signs of orbital decay or other changes. Radio telescopes will search for auroral emissions that might reveal the planet's magnetic field. And theorists will continue to refine their models, trying to match the observations and predict the planet's future. Maybe in a few decades, we'll finally have a definitive answer. Maybe we'll understand why WASP-12b is still there when it shouldn't be. Or maybe the planet will continue to surprise us, revealing new mysteries and challenging our assumptions. That's the beauty of science. The universe doesn't owe us easy answers. It presents puzzles, contradictions, mysteries. And it's up to us, with our telescopes and our equations and our curiosity, to figure them out. We've journeyed far in our exploration of WASP-12b, a planet that should be falling apart, but somehow isn't. We've seen how it was discovered, learned about its extreme properties, explored the forces that are trying to destroy it, and examined the many theories about why it's still surviving. WASP-12b is a world of extremes. It's one of the hottest planets ever discovered, with dayside temperatures hotter than some stars. It's incredibly close to its star, orbiting in just over a day, racing around at speeds hard to imagine. It's bloated to enormous size, inflated by the intense heat, with a density less than styrofoam. It's losing its atmosphere at an alarming rate, shedding billions of tons of gas every second, surrounded by a huge cloud of escaping material. It's being stretched and squeezed by tidal forces, so strong that they should rip the planet apart. And it might be spiraling into its star, doomed to fall to its death in just a few million years. And yet, despite all of this, WASP-12b is still there. It's intact, at least for now. It's holding together against forces that should have destroyed it long ago. And that survival is what makes it so important, so fascinating, and so deeply mysterious. Why is WASP-12b still there? We've explored many possible answers. Maybe it has a magnetic field that's protecting it, deflecting some of the star's assault and holding the atmosphere together. Maybe there's a hidden companion planet providing gravitational support, keeping it from spiraling inward. Maybe the orbital decay measurements are wrong, and the planet is actually in a stable orbit. Maybe our understanding of tidal forces and atmospheric escape is incomplete, and the processes destroying the planet are slower than we think. Maybe we're just lucky to be observing the planet during a brief window of time when it's still intact, but clearly doomed. Or maybe, just maybe, there's something going on that we haven't thought of. Some new physics, some unexpected mechanism that's keeping WASP-12b alive. This is the possibility that excites scientists the most, because discovering new physics is how science advances. Every time we find something that doesn't fit our theories, it's an opportunity to learn, to revise our understanding, to take a step forward. WASP-12b is not alone in its strangeness. We've seen that there are other planets like it, other worlds teetering on the edge of destruction, defying our expectations and challenging our models. KELT-9b, WASP-19b, Kepler-1658b, TOI-2109b. Each one is a mystery in its own right, each one teaching us something about the limits of planetary existence. These planets are living laboratories where nature is conducting experiments that we could never do ourselves. We can't create a gas giant planet in a lab and subject it to the heat and tidal forces of a nearby star. We can only observe what nature has provided and try to understand what we're seeing. And what we're seeing is humbling. We thought we understood planets. We had theories based on our solar system, models that seemed to work, predictions that seemed reasonable. But the universe is more creative than we imagined. It produces planets in configurations we didn't expect, in environments we thought were impossible, surviving when we think they should be destroyed. This is the nature of astronomy, of science in general. We build models based on what we know, and then we go out and test them against reality. And when reality doesn't match the models, we have to change the models. It's a humbling process, but it's also exhilarating, because every discrepancy, every mystery, every impossible planet is a chance to learn something new. WASP-12b is out there right now, 1,400 light-years away, orbiting its star, defying the odds, surviving when it shouldn't. It's a beacon of mystery, a challenge to our understanding, a reminder that the universe is full of wonders we haven't even begun to comprehend. Scientists will keep watching it, studying it, trying to solve the puzzle. And one day, maybe we'll understand. Maybe we'll figure out why this planet is still there, what's protecting it, what's keeping it together. And when we do, we'll have learned something profound, not just about WASP-12b, but about planets, about the universe itself. Until then, WASP-12b remains what it is, a planet that should be falling apart, a world that defies logic, a mystery written in starlight, waiting to be read.